Hello, operating systems people. This is Gabe Palmer, and we're going to continue talking about operating systems. We're going to pivot the class at this point into scheduling, the management of CPUs. Let's see what that actually looks like. So we have talked a little bit about how to manage a CPU. We've mainly talked about dispatching, right? We've talked about the idea that the switch routine in xv6 will do a context switch between different threads, at least in different processes in xv6. The scheduler's job is to actually decide which thread to run next. The dispatcher's job is to actually be the mechanism that changes that context, right? So this might include saving and restoring registers for sure. It might include changing virtual address spaces as well if the next and previous threads are not in the same process, right? And of course, we need to resume execution in user level after we do the switch if that's where it was executing. And these overheads are just overheads, right? They define the dispatch latency. I emphasize here that they're just overheads because remember, operating systems don't actually do many useful things on their own. They just provide services to applications that define how useful a system is. So dispatch latency is in some sense lost time within the system, but necessary for multiprocessing. Okay, so scheduling then is just the act of choosing the order of access to a certain resource by a number of principals or requests. So this is a generic definition for scheduling that can actually describe a lot of different phenomena, right? So if you go into a coffee shop and are waiting for your order, there is scheduling going on. There is something that is choosing the order of access to some resource by a number of principals. I am a principal. I'm standing in line. I am waiting to access a resource, which is the service person to help me out and give me some coffee. And the order of access is FIFO, right? Because there's typically a line, or it might be multi-queue FIFO, depending on if there are multiple cashiers, right? So scheduling is a very general phenomenon that we actually do in many different situations. We've actually already seen another situation where we essentially schedule access to a critical section. But what we're going to be focusing on is scheduling a specific CPU. And the general formulation here is that given a run queue of different threads that are all in a runnable state, we want to select one of those threads to be able to execute next. And if we're on a system that has n cores or n processors, then we want to essentially at every point in time select the n threads that are supposed to be executing in parallel, right? Now you might imagine there's different logic running on each of the cores that is in some way separately selecting which thread to run on each of those cores. There's not one unified piece of logic somewhere in the system that's telling different cores what to run. But the whole idea is that effectively we're choosing for each of the processors which thread should be running on it, right? And again, I'm going to use the term processors and processes and threads interchangeably here. I apologize. So the main question essentially that we're going to be looking at is how do we choose the next thread to run, right? Scheduling is policy, which means that it's making a decision given multiple options. And in this case, we have multiple threads that we might want to run that are runnable. Which one do we run, right? Let's start by getting some context around scheduling, right? So I want you to think about when CPU scheduling occurs. And you can see I'm messed up here. I included the wrong penny on the slide. This is a question you have to pay attention to, but I included the wrong penny. Oh, but it's okay. It's okay. She's coming, taking a bite out of the competition and is not very pleased. Okay, back to the point. When is CPU scheduling done? Within a system, within xv6, within Linux, under what situations do you think CPU scheduling occurs? Think about at least 3 of these situations, pause the video, then come back. CPU scheduling happens in a number of cases. The broad cases are as such. When a new process is created and put into the ready state, that means that it's put into the run queue and we might want to be able to execute it. Therefore, the scheduler needs to decide whether we should execute that new process or one of the existing ones. If a process voluntarily yields the CPU, we talked about this in the context of cooperative scheduling, specifically for M-to-1 threading systems, but there are yield APIs in most systems, including Linux and x86. So when a process yields, it's essentially saying, go ahead and run somebody else. So the scheduler needs to decide if you run somebody else. If a process switches from the running to the waiting state, so it was executing and then it blocks for some reason. So why would this happen, right? Think about it for a second, come up with some hypothesis, and then unpause. So we might go from a running to a waiting state effectively because we're blocking on I/O, we're blocking on some sort of a blocking system call, we're blocking on a blocking IPC to another process. Whatever it is, we're blocking and waiting on some wait queue, right? Because we no longer want to execute, the scheduler needs to decide the process to actually run. Okay, number 4, a process switches from running to ready state. When would this happen? When a process is actually running on a CPU and then switches to the ready state and is put into the run queue. Think about it for a second, pause, and come back. This might happen usually because of a timer interrupt. So if a process is running, a timer interrupt occurs, and the system decides that it's run for long enough, it's expended its quantum, then we might move it into the ready state and run some other thread. Remember, timer ticks are there to prevent a thread from going into an infinite loop and starving the rest of the threads on the system. So this is actually a really important case. Another case, when a process switches from a waiting to a ready state. Again, pause, think about when this might happen, come back. When a process switches from a waiting state to a ready state, that's effectively when it was blocked and now it's woken up and wants to execute. And that could happen for any number of reasons, but an interrupt arriving from an I/O device is a pretty good reason. An interrupt arrives signifies that some I/O has been completed. If that I/O was for this process, it might wake up and process on that I/O, right? So it's going from a block state to a ready state, a waiting to a ready state. It might also be because we woke up off of a blocking system call, a blocking IPC, whatever, right? And then last, if the current process calls exit and terminates, then of course we no longer want to run it and want to execute another thread, right? There are actually generally 2 very high-level types of scheduling. One of them is non-preemptive and the other is preemptive. Okay, so if we remove conditions 4 and 5, then we actually have non-preemptive scheduling. So that's just 1, 2, 3, and 6, right? So if processes never go from running to ready, we don't have timer ticks. And if a process never really goes from waiting to ready because of an interrupt, then we're essentially saying that there are no interrupts that impact the ordering of threads on the system, which is effectively what a non-preemptive system is, okay? A preemptive system, on the other hand, is what we basically were talking about before. It includes all of these conditions, all of the above, and it's characterized by interrupts causing concurrency within the system, right? These interrupts result in some process being moved at some point from the running to the ready state, in which case we are being preempted, right? And that running to ready state might be that it's running and goes to waiting and then goes to ready. So there might be kind of a couple of steps in the process state machine. But in a sense, when a process essentially goes from running to ready, it is being preempted in some way. So we have these non-preemptive and preemptive scheduling systems, and we'll cover both of those a little bit later, how they actually look in terms of scheduling policy. But it's important to understand when scheduling is actually run. In most systems, a scheduler is not like a specific thread or anything like that. Instead, it's just calling a function, usually called schedule or schedule, right? It's just essentially saying, look, I want to allow some other thread to be able to run now. I want to allow a scheduling decision to be made. Therefore, I will call a function that can actually implement that functionality. Okay, to understand what the policies behind scheduling do, we have to understand what their goals and criteria are, right? So let's imagine a system where we have M threads running on N cores, and of course we probably have M is much larger than N. We might have many more threads to run than we have cores. So the big question becomes, of all those M threads that want to run, which N should we be running now, right, at any point in time? And the scheduling decisions made on each individual core determine which threads are running, right, in a running state. And these scheduling decisions, as we talked about, are made on system calls, exceptions, interrupts, all of that type of stuff. So that's when a scheduler is executed. What should a scheduler try to optimize for, right? What should a scheduler try to maximize? What should it try to minimize? Penny's being very patient here. She wants you to take a few minutes here and actually think about that question. What might a scheduler, when it's trying to decide which thread to execute, what might it maximize? What might it minimize? Pause, take a little bit to think about it. There are a number of criteria that we might imagine. This is not an exhaustive list, but this is some of the main ones. We might think that we want to maximize CPU utilization, and this is simply the idea that we want to that we want the percentage of time a CPU is running a thread to be as high as possible, right? And that actually implies many things. It implies that when a core is ready to run a thread, it should run threads, but it also implies that things like dispatching latency and other overheads that might actually take away time from a thread running on the CPU, we might want to get rid of those to the maximum extent possible. Waiting time is another factor. Waiting time is effectively defined as the amount of time that a thread spends on the run queue. That is the amount of time it's waiting to execute, right? We have the response time, or the interactivity of a thread. This is essentially the time from when a thread wakes up from some sort of a block state, from some sort of a waiting or block state, to when a process can actually output data that is the consequence of its computation. So it receives some sort of activation, something to do. It needs to process on that something and then output something corresponding to it. And the latency between those 2 points, when it wakes up and when it does that output, that's a response time or later activity. Fairness is another constraint. This is just kind of the high-level idea of, are threads treated comparably? Are they given comparable execution time, whatnot? And the opposite of fairness is often some notion of starvation, where we don't have a bounded wait time or response time for all threads. I'm sorry, I use the term turnaround time here. Ignore that. So I want you to think again for a second here. What are we trying to maximize? What are we trying to minimize? So think a little bit about this, pause, come back to it. Okay, we tend to, of course, I actually had a Freudian slip and said that we obviously want to maximize CPU utilization. We do. We tend to want to minimize wait time. If you can execute something all the way through with no waiting, then it will have much better properties for that thing. But waiting time could also be viewed as a global property, where we want to minimize the waiting time of all processes in the system. So we tend to want to minimize waiting time. Response time or interactivity, we do often want to minimize this. We want to make sure that the time between when you touch your screen on your phone and you drag your finger to when it actually shows the screen being dragged down, we want to minimize that, right? There's a certain notion of interactivity that's very important and is optimized for on mobile devices quite a bit because of this. Next time we'll talk about some of the human factors involved that motivate that. Fairness, we tend to want to optimize for. We want to maximize it. We want all things to be treated the same, all other things being equal. But there are many situations where we want to either prevent fairness and allow starvation, or we want to have a more nuanced version of fairness where not all threads are exactly treated equal. And usually when we do want to minimize starvation, right? We want to get rid of starvation entirely. But again, there are some cases where you might not care about that. The next question that we really want to ask, this is a lot of goals, a lot of constraints for a scheduling algorithm, a scheduling policy to optimize for. So to get a little bit more of a sense of what we're really trying to do here, it's important to ask if applications can give us some guidance that can tell us what constraints we should optimize for. It's very hard to make a single scheduling policy that can do all of these things. High CPU utilization, good fairness with absolutely minimal waiting time, the bare minimum response time. It's really hard to make a single policy that does all of those things. So can we actually ask applications to give us some guidance for which ones of these we should optimize for? And for those of you who harken back to the first lecture and remember exactly how I think about systems with the applications being the bun, indeed, this does mean that we're trying to reach up to that bun and say, hey, you empty starch, tell us what you need, right? Okay, so let's gain a little bit of an intuition about this. So here you see two different application classes. So on the left, you see a very primitive version of the X Windows system. Believe it or not, the X Windows system running on Linux today is still the same code base as existed here, with some of its core pieces replaced, obviously, with just another window manager placed on top. We're still using technology that at some point looked like this. And then we have Bitcoin on the right? If we think about what's happening on the left, then we have people typing at a keyboard and waiting to see things on the screen. If we think about what's happening on the right, when we're mining for Bitcoins, we're doing a lot of heavy computation, right? So on the left, we're waiting for I/O. The X Windows server is waiting for I/O from the keyboard or the mouse, trying to compute relatively quickly and output to the frame buffer any changes that might have occurred. On the right, we have Bitcoin that's trying to, do computation to mine for Bitcoin, then, do more of that, and then hopefully after many iterations of just doing computation to profit, right? So if we think about what we'd want to optimize for these two applications, we'd care quite a bit about the responsiveness of the X Windows system. We want the latency between when we hit a key on our keyboard to when we see the effect of that being output onto the screen being as minimal as possible, right? Whereas for Bitcoin, we probably want to maximize utilization of the system, minimizing all other overheads in the system so that we can compute as much as possible and mine as quickly as possible, right? Having Bitcoin mining on the same system as the X Windows system, you can imagine might be a little difficult for a scheduler because it wants to minimize the responsiveness while maximizing the utilization. That's going to be a hard balance to be able to achieve well, right? Okay, let's look at another application domain to get a little bit more intuition about this. This is a 3-tier web serving system. 3-tier means that you typically have web servers, proxies, receiving client requests. Those send off those requests to application servers, the second tier. Here I'm using Node.js as an example, but you might have Python technology or Ruby on Rails or something like that. And then you have a database, the third tier, kind of backing all of that business logic, right? So Nginx is a web server. It essentially waits for a networking request, serves some static requests that it can, but for any dynamic requests, pass those off to Node. So it receives a request, does a small amount of computation, and then does some output to talk to Node. Node, on the other hand, receives these requests and then does some pretty heavy-duty computation on them, right? This might be image processing for trying to do face detection or something like that, or some heavy-duty business logic to be able to, implement Amazon or something like that. And then on the back end, we have the database that's essentially waiting for an SQL command, executing it, interacting with the solid-state device, your disk, effectively, and then returning replies to the business logic. So Nginx, simplifying it, is waiting for network I/O, doing quick computation, and then forwarding that onto the middle tier, the application servers, which are receiving a request, are doing some pretty often compute-intensive computations and sending queries to the database. The database is actually doing a lot of processing. Databases, especially in the modern times where we have a ton of memory, are able to do a fairly large amount of processing and keep CPUs saturated. And we typically want very large, beefy database processing machines, so they're often many, many cores. So they do a lot of processing and I/O when necessary, right? So if we look at what these three different applications are really optimizing for, we might think that the front tier, the web servers, are optimizing for responsiveness. The application tier are optimizing for utilization, where we just want to be able to do as much business logic as possible. And the back tier, the database tier, often care a lot about utilization, letting the database do as much as possible, but also minimizing the waiting time of the database in the system, right? So here we have kind of minimizing the waiting time of a specific application, not necessarily of all applications. So you can see that we have this notion of kind of having some applications that are very what's called I/O bound, right? This is Nginx, this is the X Windows system, right? They really focus on responsiveness. And then we have more CPU bound applications that are focused much more on efficient computation or high utilization, right? So we tend to think about these two classes of applications when we're trying to schedule effectively. And we can see that it requires that our scheduling policies optimize for different things. Now, let's start with the simplest possible scheduling policy and kind of build from there. This building of more and more complex policies will continue into the next lecture. So the simplest possible policy for scheduling on our CPUs is first come, first serve, right? This is kind of the scheduling equivalent of FIFO, first in, first out, where the first thing to ask for, in this case computation, gets to execute, and it continues until it's done executing. Now keep in mind, this might not, again, be kind of like the till a process has executed it exit. It could be till a process blocks and therefore is no longer in the run queue, right? So first come, first serve is one of the simplest scheduling policies because it just kind of keeps the processes in order and executes them as such. And it is non-preemptive. So it will not preempt a process while it's executing and trying to execute to run another one. It will just keep running the first process that requested execution until it blocks or terminates. So here we have three processes, P1, P2, P3, and let's imagine they have three different burst times. A burst time is just a notion of how long that application or that process is going to execute currently, right? This is not something that the scheduling policy actually knows, right? It would have to tell the future for how long this thing is going to execute before it blocks. So burst time is essentially how long it wants to execute before it blocks next or terminates. Now, if we assume that the processes arrive in the order of P1, then P2, then P3, the schedule, if we have a scheduler using first come, first serve, would look like the boxes below, where at time 0 on the left, we execute P1, which then runs on the system until time 24, because that's how long its burst is, and at that point, we'd execute P2 for the next 3 time units, and then P3 for the last 3. Right? So this is just a way of kind of laying out the processes one by one as they execute, right? Now, the waiting time for P0 in this case, let's actually look at waiting time now, is P0 is 0, right? P0 had to wait on the run queue for 0 time units, right? P2, however, was on the run queue waiting for P1 to execute for its full 24 time units. And P3 was even worse. It had to wait for the execution on the run queue of both P1 and P2 for a total of 27 time units, right? So if we take it, those are the wait times of each of these processes, and if we take the average of the wait times, it's 17. And given that P2 and P3 are very short burst times, it means that they were waiting for an extremely large amount of time, proportional to how much execution time they actually had, right? So we see that first come first serve has some weird artifacts here where it can cause some very high wait times even for fast executing applications. And we can really see this if we assume that the processes arrived in a different order. P2, then P3, then P1, right? So the very expensive one, P1, executed after the other two, right? So in this case, we see the schedule lying out as follows, right, in the blue nodes. So we have P2, then P3, then P1, and because P2 and P3 are relatively quick to execute, each of them executing for 3 time units, they execute first, then P1. If we look at the wait time for each of them, P1 is actually not that high. It's just 6 time units because it had to wait for both P2 and P3 while it's in the run queue. P2 had 0 wait time, it got to execute immediately, and P3 only had to wait for P2, so 3 time units, right? So if we look at the average waiting time now, we see it's actually 3. So in the previous case, we saw an average waiting time of 17. In this case, we see an average waiting time of 3. And this is intuitive. If we have a non-preemptive scheduling algorithm, then the order in which the processes arrive and how long very specifically they take to execute has a big impact on all of those waiting behind them. And this is called the Convoy Effect. You can imagine if there's some sort of ravine in between 2 cliffs, and you can have a caravan of cars driving through it. Think Mad Max style, right? If you've seen those shows or those movies. And you have the first car kind of going into the caravan and then everybody coming after it. And you can't really pass in a ravine, right? So how fast that first car is has a massive impact on the rest of the cars, right? So this is kind of the intuition behind the Convoy Effect. You are going to be heavily impacted by all of the threads that happen to be in front of you, right? So this doesn't really feel very good, right? It definitely is not great for having a predictable waiting time. But I'd like you to think about how this behaves in terms of fairness, starvation, and in terms of interactivity and responsiveness. Think about it for a second, pause the video, come back. So in terms of fairness or starvation, fairness, it's really hard to actually assess it. In some sense, it is giving, the policy itself is giving no privilege to one process versus another. So in some sense, you could call it fair in an intuitive sense, but in another sense, it can let one process obviously heavily impact the execution of the other. So in that sense, it's not very fair. So it's very hard to actually state whether this is fair or not. Fairness is a little bit more of an intuitive definition. However, for starvation, this is clearly bad. If any of the processes that are lined up in front of you goes into an infinite loop, you never get to execute. Any thread never getting to execute means that they're starved, which is bad, right? In terms of interactivity and responsiveness, it heavily depends on how the processes actually line up, how responsive they are, right? In this example, relatively responsive. In this example, very much not responsive for P3, for instance, right? So this is not a good policy for optimizing for interactivity or responsiveness. Sometimes it might accidentally happen, but that's not an optimization for a goal. That's just kind of, failing into a goal sometimes. Okay, so given these, but there is actually, I should point out, there's a big benefit to first come, first serve. And that's that it very much minimizes the overheads within the system. If we think about dispatching overhead and context switching overhead as stealing from the execution time of the processes in the system, this actually minimizes the context switches in the system, right? So it, in some sense, does maximize the utilization of the system. So this is good for some applications and is used in some applications. If you have applications that need to really just use 100% of the CPU and preemptions could hurt them significantly because, for instance, they use almost all of memory and preempting them would mean really shuffling all of that memory out to disk, which is heavily expensive, then first come first serve is absolutely used. For instance, when you're scheduling supercomputers, first come first serve is often, well, at least traditionally, the de facto scheduling policy. Okay, but let's relax it a little bit, right? Let's add preemption, right? Round-robin scheduling is the idea that time-sharing systems do want to provide some sort of a fair distribution of the CPU resources, even in the presence of infinite loops for different processes. So a non-preemptive policy doesn't really cut it, right? We definitely want one thread to not be able to monopolize the CPU, therefore causing starvation for other threads. So round-robin, you can really think of it as just first come, first serve plus preemption. And the preemption policy is essentially that when a timer tick comes in, the the process at the head of the queue moves to the end of the queue. So you just have this cycling through all of the processes. So we have this notion of a quantum. A quantum is the amount of time that we allow a process to run before we switch to another process, right? So each process executes a single quantum before it's preempted. Preempted threads are placed at the end of the run queue, and this absolutely requires a timer interrupt to measure these time slices and see when a quantum has expired so that we actually cycle the process at the head of the queue till the end, therefore allowing us to execute all of the threads in turn. So if we imagine that there are T threads in the run queue, we also imagine that we have a time quantum of Q. So I'm going to call the quantum that we're using Q, right? Just want to check. Okay, great. So we have this time quantum Q, and we can actually start analyzing the fairness of the system. So the fairness of the system actually kind of boils down to us all getting equal share of the CPU, and if we're all trying to use a CPU at all points in time, then each thread will get 1 over T of the CPU in chunks of size Q. Right? Again, if we have T threads, let's say we have 3 threads. That's essentially saying that we get 1/3 of the CPU in chunks of size Q, right? So if we assume Q is 10 milliseconds, then we essentially get to execute 10 milliseconds for every 30 milliseconds because we're getting 1/3 of the CPU. We can also actually start thinking about what response time might look like. We can say that the wait time of a thread over time, and you can see the diagram here with the blue and the yellow, time is proceeding as we go to the right, and each of those slots in the graph is a queue, is a quantum, right? So what we see here is that if we execute our thread for 1 quantum for 10 milliseconds, then we have to let the other 2 threads in the system execute for the next 2 quantum, and then we get to execute again. So we have to wait for 2 quantums for 20 milliseconds before we get to execute again, right? So the amount of time that we have to wait in between our quantums of execution is essentially T minus 1, basically 1 for each of the other threads times Q, right? Okay, so we can actually start saying something concrete about the wait time in the system, the responsiveness of the system, because we know that we get to execute 1 out of T quantums. So we can actually start saying concrete things about those optimization goals, right? And we now need to start thinking about, okay, we can say concrete things about the goals, but what about some of these constants that we're choosing? So what about the size of Q? If Q goes to infinity, then we essentially have first come, first serve, right? Q of infinity essentially means that we're never doing preemptions and we have first come, first serve. So that's interesting. Round-robin scheduling actually generalizes first come, first serve scheduling. So when one algorithm generalizes the other, it means that the other is describable by tuning one of the parameters of the first, right? So Q is a parameter, we can tune it to infinity to describe first come, first serve with round-robin scheduling. So that's cool. But what if Q is 0? Obviously, Q of infinity has bad properties. First come, first serve has bad properties. So if it's really large, that's bad. If it's really small, is that good? I'm going to ask you to think about that for a second, but I'd also like you to think about the question of what values of Q give us the best fairness and the best throughput, okay? So pause, think about it for a second, and we'll come back. Okay, so if Q is 0, that means that we're essentially not really executing threads for any time before we switch to the other thread, so that doesn't work logically. If Q is 1, we allow quantum to be one cycle. Then we would execute for a cycle, switch to another thread for another cycle, switch to another thread for another cycle. The dispatching overhead ends up overwhelming any of our execution, right? So very low values of Q are not tenable, are not useful. Very large values of Q are not tenable, are not useful. So the question is, what's just a practical value of Q that we might be interested in, right? So it's also interesting to ask again, what's the best fairness? Well, very large values of Q don't feel very fair because you can have starvation. Very small values of Q seem to be more fair, right? But you're paying for that fairness in terms of utilization because dispatching overhead is significantly higher. So the next question, best throughput, that comes down to high utilization, right? Throughput is we want to do as much work over time, as many as many cycles of execution of our applications as possible. If we have a lot of dispatching overheads in the system, we do not have high throughput. So again, low Q, bad throughput, high Q, bad fairness. You know, what can we do here, right? There has to be some sort of a Goldilocks solution somewhere in the middle. Hold on a second. Let me make sure I didn't just kill my recording. I did not. Great. Okay. So let's just go through an example here to make sure that we really understand what's happening. So if we assume that we have a round robin with a Q equals 3, so we have a timer tick and 3 timer ticks is a quantum. Here we have 4 processes, P1, P2, P3, and P4, and we know that we know, you and I know, but the scheduler doesn't necessarily know how long it's going to execute. But we know that they're going to burst for 6 time units, 3 time units, 1 and 7, right? So if we look at what that looks like on the kind of shoddily made graph below, we see that if we assume that they arrive in the order of P1 to P4, then P1 executes first. It will execute for 3 time units, and then a quantum has expired. So we move it to the back of the run queue, start executing P2. And P2 actually finishes its execution within 3 time units, so its quantum expires at the same time it's done executing. Therefore, we can stop executing it, move on to the next process. It is no longer in the run queue, it completed its execution. It probably blocked waiting for I/O or something. Then we run P3. P3 only executes for 1 time unit, so it completes its execution before a quantum even expires, so we're able to go on to the next process in the run queue, P4, and execute it. P4 executes for a long time, but of course, after 3 time ticks, it's quantum, we preempt it and run the next thread in the run queue while moving P4 to the back. Now you'll notice that we essentially are going to go back and execute P1 again. It was put at the back of the run queue initially. Now we execute it for its next 3 time units, which actually finishes its execution. It executed its first 3 time units initially. Now it's executing its second 3 time units, and it completes its execution. At that point, we run P4. P4 will finish a quantum, but because P4 is the the only thread in the queue at that point. We just continue executing it until it executes its 7 time units, right? So if we look at this in comparison to FIFO, and we look at the responsiveness of each of the threads, P1 would actually have a much lower responsiveness in FIFO. It would just have 6, right? Because we would execute P1 till completion. Here, P1 finishes at time 13. So P1 actually decreases in response time, right? However, P4, and P4 is actually the same in either case, right? It kind of finishes last, so its response time is 17. It's kind of a wash either way, right? But P2 for FIFO would have a response time of 6 plus 3 because it would have to wait for P1 to compute, so 9, right? So, okay, let's compare that with what's happening here. P2 actually finishes at time 6 with round robin. So it actually has a better response time by 3 time units in this situation. In FIFO, P3 would have a response time of 6 plus 3 plus 1, which is 10, right? In round robin, in our example here, P3 finishes at 7. So again, has a better responsiveness. So in this case, 2 of the tasks have a better responsiveness, 1 has a worse responsiveness, and 1 has an identical responsiveness, right? It's not clear that we're always improving the situation in terms of responsiveness, but what we are doing is making the responsiveness more predictable. An infinite loop of an early process cannot completely kill the responsiveness of a later process in round robin, right? So we're getting more predictability of responsiveness. Okay, now we want to ask the question of what should a quantum be, right? And how does that kind of trade off versus the response time in the system? It may be surprising to you. It was certainly surprising to me, but a lower quantum, a smaller quantum, does not always lead to better response time. So the average response time can actually go up for a smaller quantum. It often, on average, will go down, but it's not a direct relationship. So let's try to just get a little bit of an intuition as to why that is. I don't want to prove anything here because I don't think it's that illustrative or that interesting. So let's just get a response time for it, okay? So let's assume that our thread is going to execute for a burst of B, and we have T threads, the same as before, right? And we see at the very top in the diagram, the burst being slightly larger than a quantum, taking more time ticks than a certain quantum, right? What we're going to look at is the remainder. The remainder is actually one of the key factors here for deciding if the response time is better for a different size quantum. So the remainder of that we're talking about here is the remainder of the burst time modula the quantum. And that's essentially saying we know that the thread is going to have to execute for a number of quantum, but then the question is, how much more will it need to execute before it finishes in that last quantum that it's executing in? If that last quantum's worth of execution is exceedingly small, is very small, 1 time unit, then it might have been better to have a higher quantum so that it will finish as opposed to being delayed by many quantum of the other thread's execution before it. Okay, so we know the remainder. The remainder is essentially how much it needs to execute in the last quantum of its execution. We also have just the normal division, which is essentially how many quantum, discluding the remainder, this thread needs to execute in. So in the example at the top right, we see that the division is 1. We know that we're going to need to use 1 full quantum for the execution of this thread's burst, while the remainder of its execution falls partially into the next quantum, right? So we can calculate something like the minimum response time that we could have with a relatively simple equation of TQ times D plus R. Let's dive into that a little bit. T times Q is essentially just, all right, I know that I'm going to have a number of quantums of execution before I get to the point when I'm going to be able to complete and execute my remainder. So how many quantums of execution are going to be before I get to that last quantum where I execute my remainder? Well, it's basically how many threads are in the system times their quantum, how long they execute, and D is how many of these quantums we need to execute for this given thread. So it's essentially, well, looking at the graph on the bottom, I know that I need to execute one quantum worth of full execution, and I know there are 3 threads on the system. So if I get to execute my quantum first, then I need to wait for the next 2 quantums worth of execution for the next 2 threads. Then I get to execute my remainder. The difference between when we started and when the remainder terminates is the response time min that we have the equation for there. And we're essentially saying, well, how many of these kind of 3 different quantums lined up for all the threads do we have to wait for? And then add the remainder onto that. And that's what that response time equation is. We can also actually calculate the wait times as we kind of saw before, right? So the intuition here again is if we choose our quantum to have very small remainders, then we're essentially having to wait for all of these quantums worth of execution before we execute that very small remainder. However, if we choose the quantum to be a very small amount larger, maybe we won't have a small remainder requiring us to wait for all of the other threads ahead of us to take their turn in round robin, and we might actually have a better response time. So this is the intuition as to why sometimes a lower quantum actually leads to a slightly higher response time, right? And again, if a queue is very large, a quantum is very large, we have FIFO convoy, so that just is never good. So we tend to practically choose quantums based on essentially dispatch and context switch overheads. If our dispatch and context switch overheads, let's say, take a microsecond, and we only want 1% of our CPU overhead to go to those overheads, then we might choose a quantum of something very, very small, like 100 microseconds. Often systems don't need to have that fast of responsiveness, that fast of a turnaround time for all of the processes. So they tend to choose around 1 millisecond to 100 millisecond quantums. Okay. Now, this is investigating FIFO and round-robin scheduling, but there's also a large variety of other scheduling policies based around priorities. So in this case, we're actually trying to not execute threads fairly. Instead, we're associating them with a priority and effectively telling prioritizing some threads over the other. If they both want to execute, we will always choose the one as a scheduling policy that has the highest priority, right? So the scheduler always selects the thread with the highest priority. There are preemptive and non-preemptive variants of priority-based scheduling. The non-preemptive variants are more interesting than for FIFO because you can avoid starvation now. A low priority thread executing non-preemptively. If we allow preemptions between priorities, we'll allow a high priority thread to execute. But that's a question. Now we need to answer the question of, do we allow preemptions between threads at the same priority? No, if we're doing non-preemptive. But do we want to allow preemptions between priorities? If the answer is no, then you don't really have that great a system because, again, low priority threads can starve high priority threads. That's real bad. But this is a decision that you have to make. So the general problem with priority-based scheduling is essentially starvation, right? Low priority processes may never execute. This is what we're trying to avoid with round robin by allowing everybody to get a chance. But it sometimes is the case that some things should have a higher priority. Maybe they require heightened responsiveness, therefore they should have a higher priority, right? I do want to say that priority does not map well onto our intuitive notion of kind of importance. priority and importance are not necessarily the same notion. There are some systems that treat the criticality as the same thing that we would think of as importance. But sometimes an important thing to compute doesn't really require that good of response time, so we don't really care about it having a high priority, right? So long as it can't be starved by the other things that are less important. So one solution is aging. And if we want to have priority-based scheduling, but we want to avoid starvation, then aging is the notion that as something executes with a high priority, if it executes for a long time, we can age it and move it into lower priority bands. And this is how a lot of Unix-based systems did scheduling for a very, very long time. Correspondingly, if something has a low priority, for a very long time, we might escalate or elevate its priority over time to guarantee that it's not starved, right? There are kind of two different ways to think about doing this type of thing. So priority-based scheduling, there are many ways to do it. I want to give one example. We're going to go over another example next class. Multi-level queue scheduling is one example. And multi-level queue scheduling is a way that we use priority without aging in most cases. And how we think about this is that the ready queue is partitioned into separate queues, one often per priority. Each queue might have its own scheduling policy. So we might have a queue for IO-bound or interactive tasks, and that might use something like round robin, right? And we might have a queue for CPU-bound or background or batch tasks. These are ones that you don't really care about the responsiveness at all. You just want them to be fast. So we might use first come first serve for that queue. There were systems in the past that actually allowed the user or asked the user to classify the applications you are running into these different classes, IO-bound, CPU-bound, whatnot. The problem is it's actually a little hard for the user to do that. Like, would you say that your web browser is IO-bound or CPU-bound? Sometimes, honestly, it's IO-bound or sometimes CPU-bound. It depends on what the JavaScript is running on it, but you don't know what JavaScript is running on it. So it's not a good policy to have the user provide this information. However, sometimes the system designer can provide some of that information. The X server, for instance, we know is interactive, so maybe they can kind of give some intuition of that to the operating system scheduler. Okay, so each queue might have its own policy, and we essentially schedule between queues. Now, the intuitive way to do this is that some queues just have a higher priority than the other. So if we do have an IO-bound or interactive queue that's round robin, maybe we always schedule it with a high priority, right? The downside of that, of course, is that if your IO-bound task goes into an infinite loop or just executes a huge amount of time, then the background tasks are going to be starved. So we're back to starvation, right? Another technique that a lot of systems, including Linux, use are allowing proportional allocation, which is to say that you might use priorities in the common case, but ensure that the background, that second queue, gets 20% of the CPU. So this essentially just prevents starvation in a very kind of sledgehammery way. Linux actually does use this approach. So multi-level queuing is the de facto, this is the scheduler in Linux. So we have tasks that are higher priority. We have run queues that are higher priority, and Linux allows FIFO scheduling. So there is a FIFO scheduling class, as it's called in Linux. And you can, if you're root, tell Linux to move processes into that FIFO class. And yes, if it goes into an infinite loop, your system is completely and utterly hosed. It's high priority. You can literally not even type at your keyboard anymore, right? We also have fixed priority, which is a lower priority run queue than FIFO, and that is round robin. Has a fixed quantum at which it switches between different tasks. Modern Linux also has a dynamic priority set, which is of lower priority than round robin, but higher priority than best effort, and that's running earliest deadline first, EDF. That I'm actually not going to go into in much detail. We'll talk about it a little bit next time, but it's basically a real-time scheduling policy that ensures bounded response times. Best effort is the typical way that we're scheduling. Almost all of the tasks on your Linux system, on your Windows, on your OS X system are scheduled using a best effort scheduling class. So it's lowest priority, and that implies that essentially most normal systems don't use the top 3 run queues. They don't actually have tasks that are scheduled using those, right? So we're typically using only the run queue at the bottom, which is best effort. Best effort means that it's not trying to make any guarantees. It's just trying to run all of the applications as well as it can, right? It's not even guaranteeing no starvation. It's just, the policy is trying to avoid it, right? So this tries to essentially fairly schedule between threads while also trying to optimize for I/O bound tasks to have good responsiveness, right? And notice that those 2 goals are actually in contrast. If you're prioritizing I/O bound tasks to optimize for your responsiveness, you are inherently prioritizing it, therefore not fairly scheduling between different threads. So this makes scheduling a little bit of an art for best effort systems. But I want to back up a little bit. We're talking about multi-level queuing, and that implies that if these 3 scheduling classes at the top execute at a higher priority, they absolutely can cause starvation for that lower priority run queue. That does actually happen. Now, there's definitely a question of how you actually place threads within these queues. As I just talked about in Solaris and in Linux, there are commands to explicitly place threads into these different queues. Typically, you have to be root to be able to do it, so you have to be quite privileged. But there are systems, even those that exist, I believe that BSD is still using a variant of this, FreeBSD, that actually use multiple queues and have different policies for moving different tasks between the queues. So they try to answer the question of how do you make a thread to queue mapping by actually dynamically moving the threads between the different queues. And the whole idea here is that we want interactive and IO-bound threads at a higher priority and therefore in queues that are scheduled with a higher priority. But if they execute for too long, then they no longer are probably IO-bound tasks and are starting to behave more like CPU-bound tasks, so we should demote them into other queues that are of lower priority. So now threads can move between the different queues, and we use aging to avoid starvation. If a thread executes for a long time, it will do so with a higher priority until it gets demoted into queues that are at a lower priority. And then the other threads that might have been starved up until that point will be able to execute. So multi-level feedback queuing has a number of parameters. These are like how many queues do you actually have in the system, what scheduling algorithm do you use for each queue, how do you promote different threads between queues, how do you demote threads between queues, and what queue should a thread enter into the run queues in. So there are a lot of questions here and a lot of no good answers, I'll put it that way. Everything is a heuristic algorithm here. They aren't necessarily based on science or on kind of math. They're often based on just kind of what ends up working. It's kind of an art to design a scheduling algorithm because there's no one configuration that satisfies all requirements, but there are configurations that feel better as you run a system than others. So let's go through an example where we have 3 queues with one quantum time unit. So we have the high priority queues, which is Q1, which is using round robin with a time slice of 8 time units. And I messed up here. I should have said that the quantum is 8 time units here to remain consistent. I apologize. So we have... No, I was right the first time. I'm sorry. So we have a quantum of 1 time unit, and we are executing on round robin, and there's going to be kind of 8 time units associated with that queue. We have a lower priority Q1 that has 16 time units associated with it, also running round robin, and we have Q2 at the lowest priority that's actually running first come first serve, right? So new jobs will say arrive at Q0, and they run using round robin with a quantum of 1 with all of the other threads in that queue until they expend these 8 time units. Once they expend 8 time units in that queue, they're starting to look a lot less like IO-bound tasks because they're doing a lot more computation and a lot more like CPU-bound tasks, so we will demote them to queue Q1. Once in Q1, once they run 16 time units, then they decay and are demoted down to first come first serve Q2, which is at the lowest priority. At that point, we assume that they're CPU-bound tasks and schedule them as such, right? Now the question is, can this cause starvation? And it's actually maybe not very intuitive to actually answer that question, right? The answer is they actually do cause starvation, or can cause starvation. And the idea here is because once a task is in the first come first serve queue, it's there forevermore, which is not necessarily a problem in and of itself, so long as those things that would starve it also get placed in the first come first serve queue. But if we have a constant stream of threads that unblock, go into the run queue, and are placed in Q0, execute for some amount of time, and terminate, but before they terminate, before they block, the next thread comes in and is placed at Q0. So we just have this constant stream of threads going into Q0. Then we could have starvation of the threads in both Q1 and Q2, right? So we can actually have starvation here. And of course we can have starvation because Q2 uses first come first serve, but that's maybe not the interesting case here, right? Okay. So you typically need some sort of a promotion scheme as well to make sure that you can kind of go up from Q2 to the higher queues in some way after you haven't executed for some amount of time. But you can start to see this is all getting a little hacky, right? Scheduling policies are usually not very clean. Okay, so this is an intuition about how scheduling policies are made. Next class we'll go into a real scheduling policy used in Linux. I say real. A lot of what we've gone over so far are real policies used in many operating systems, but we'll go over Linux's next time. The last thing that I want to touch on is something that I alluded to at the start, which is this notion of multi-core scheduling, right? I've been talking essentially about what if you have a run queue and one scheduling function that is deciding what to run, right? So intuitively, that's kind of a single core making decisions, right? But of course, when we have multi-cores, we also need to schedule on now not just one CPU, but multiple CPUs, multiple cores, right? Remember, I'm using cores, processors, and CPUs in an interchangeable way. There are differences. Go back to the FAQ to see what those are. Okay, so the scheduling logic, the scheduling policy, executes code on each core. And it essentially, again, executes whenever system calls, exceptions, interrupts come in that basically call the schedule function, right? There's no like scheduler process or anything like that. It's just a function that you call when you no longer want to execute, or you might want to wake up, or you might want to run a thread that was woken up, right? So that's essentially just answering the question, which thread should I run on my core, right? But this actually implies the question, on which core should a thread run, right? So how do we actually implement this? How do we decide which core a given thread should run on? So think about this a little bit, try to come up with some brainstormed ideas. Pause, come back. Okay, so one way to think about this, and I'm going to give kind of polar opposites and then dive into kind of the more nuanced approach. One way to think about this is with partition scheduling. And what you see on the right is 3 gray cores on the top, each of which might call a schedule function, which then needs to access its run queue. And the run queues are the purple queues below, right? So partition scheduling essentially says that each thread is assigned to a core. And therefore, the scheduling run queues of each core are completely separate. Therefore, each core only needs to look at its own run queue. So this is relatively simple, right? Global scheduling, on the other hand, says that we share a single run queue amongst all of the different cores. So you can see that here, all of the 3 cores share the same run queue, right? So each thread is considered by each core. Therefore, a thread might run on one core at one point in time and another core at another point in time, right? So what are the trade-offs with this, right? Penny is almost out of attention, right? This is a long one. I apologize. Little girl. We're almost done. Okay. Don't worry, Penny. Pause, think about it. What are the trade-offs between these? Okay. So for partitioned scheduling, where each thread is assigned a core, therefore the run queues are completely separate, we have a problem that we might have a situation where our utilization is not very well maintained. And the case here is when some core has at least 2 runnable threads that it can execute, while another core, in this case core 1, has 0 runnable threads. So now core 1 can't run any threads because its run queue includes none. But there are threads that want to execute in the system and are not loaded onto a core, not actually running at the time. So we are wasting utilization of the system, right? So in the picture on the right, the left core wants to run something but can't, therefore it cries instead of doing something useful, whereas the other cores actually have work that that core could be doing, but in partition scheduling, you just can't do it. Partition scheduling is actually very common, believe it or not, in some systems, in specialized systems. And the essential reason for that, and this is, in specialized systems, the reason for that is because synchronization is trivial. So we don't really need to synchronize at all, right? The data structures that we're accessing for the run queues are partitioned between the different cores. So we never have a case where one core wants to access another core's run queue, therefore we don't need to protect them with locks. So we don't need any locks in the system. We have no synchronization overheads, and that can actually lead to a higher effective utilization. So if somehow the workload is balanced between the cores, which is to say that essentially they all have threads to execute at every point in time, this can actually have a higher effective utilization because there's no overheads from synchronization, right? Global scheduling, on the other hand, has a higher effective utilization in the sense that if a core wants to run a thread, it will be able to run a thread so long as there are any threads in the run queue, right? If there are any runnable threads, it will be able to pull it off of that global run queue and execute it. The downside is that we essentially have to have a single lock protecting that run queue. So we have a single lock for all of the cores. You can imagine if you have 4096, 4000 cores, all of them hitting this run queue every timer tick is going to cause a massive amount of synchronization overhead, right? And that is a really, really big problem, right? So this can actually lead to a decreased utilization for the system due to the increase in synchronization overhead. So again, it's not necessarily a question of which is better, partition versus global. It's more so a question about what is your workload? Is it consistent? Can it be partitioned with a high confidence knowing that we'll have something to run at all points in time? Are we running the scheduling logic frequently and therefore need to synchronize frequently? These are all the questions that you need to ask to decide which one is better, right? However, I do want to go one step deeper in analyzing this because there's a very, very subtle issue. And the idea here is that there's this notion called thread migration. And thread migration is just the idea that when we're running a thread on one core, its data gets pulled into that core's cache. If it's blocked or put into the run queue, and another core decides to now run that thread, then when it runs that thread, it will be using a different core's cache, and therefore all of that thread's data will need to migrate from the previous core's cache into the new core's cache. We don't really understand what that means right now, but take it for granted that moving data from one cache to another is a really expensive operation. Take advanced operating systems, and we'll go into this information a lot, into this detail a lot. This can take on the order of 1 to 5 milliseconds worth of overhead. So if we are migrating threads between cores frequently, then we're actually massively hurtling the actual utilization of the system. So this is a really, really big problem with global scheduling. So what Linux and what real operating systems typically do is they use partition scheduling. But if you end up unlike in partition scheduling as I presented it, we actually have a lock for every run queue. And if in the top diagram, we have a core that wants to run a thread, but its run queue has no items in it, no threads that are runnable, then it can look over at another core's run queue, take that core's lock, and steal one of the threads and put it into its local run queue, right? And in doing so, we have to have locks for each of the run queues, and there is some amount of synchronization overhead when we have this case where we want to migrate a thread from one queue to another, right? So there is absolutely overhead for synchronization to do that. But the idea is that this act of migrating the threads only when there's nothing to do will balance out the workloads between different cores. And if we balance out the workload, that will decrease the number of migrations in the future, therefore making execution behave more like partitioned scheduling, where we are not necessarily taking the locks of other cores' run queues at all. Right? So this avoids a single global lock. We do have per core locks that are taken by other cores, but hopefully infrequently, only in these rare cases where migrations need to happen, and we're using hopefully partition scheduling most of the time. Right? So this gets really complicated, but this is literally how real systems work, right? This is Linux, Windows, OS 10. Okay, so the summary, I'm sorry, this was a long one, is that system schedulers essentially need to optimize for multiple goals in the system. Policies essentially need to make trade-offs between those many goals. In essence, they need to balance which goals they want to pay attention to at what points in time, given what they're executing on the system. And this often means that they need to try to at least implicitly classify systems as IO bound or CPU bound, right? And these trade-offs also apply to multi-core systems, right? Essentially, we are trying to maximize the utilization, but in doing so, we might hurt it effectively by using global versus partitioned. So trade-offs appear everywhere in systems. There is no optimal answer. There's only the question of what is your workload and what are you optimizing for, and therefore what policies should you use for that. Sorry, this is a longer recording. Hope you enjoyed scheduling. We will continue talking about it next time. Have a good one. Bye.